Oops, no. Is the audio working now for people online? Okay. All right. Okay. So last class, we saw this theorem that NAND circuits in general for any Boolean circuits, if you have n variables and you have one output, and as long as the number of gates is at most s, you can encode them as binary strings, 0, 1 star strings, where the length of the encoding is at most this bound, right? The constant is not important. The main thing is kind of think of it really as s times log s, except in some pathological cases, most of the time you can imagine that the size of the circuit is at least the number of variables. In fact, the textbook adopts this convention that S is always at least n, but we are just going without it. Yeah.
What do you mean when you say except in some pathological case?
I mean, most of the time, if you have, if you have a variable, you would like it to appear in something involving the circuit. Okay. I shouldn't say pathological, but except for a few cases, you would expect the variable to kind of play a role in the computation. Okay, that's what I meant. Right. And yeah, there's a lot of nitpicky things about how you define Boolean circuits. In fact, when the textbook adopts a slightly different convention, but I think this is a little bit easier for us. So we are sticking to this. Okay. And we saw this result in kind of, building the encoding in one step at a time, right? We first converted to this representation as a kind of sequence of integers. And from there, we used our bag of tricks from on compositions to get it. Okay. And then we use this to get our second sort of big theorem, which is a way to count the number of functions computable by circuits of certain size, right? This sounds complicated, but we said, okay, the number of circuits is bounded by at most the number of strings of this length, and that is just 2 to the whatever length you have. Okay, any questions about these two things that we discussed from last lecture? Okay, if not, what we're going to do today is first is to use this to prove circuit lower bound. Okay, so again, as a reminder, we were trying to show something like this, right? So this is due to Shannon in, I think, 1949. I can check it up later. That there is some constant c greater than 0 such that there exists a function on n bits that requires c times 2 to the n by n many gates. Okay. As long as n is sufficiently big, there is a function which requires at least these many gates. Okay. And as I said, this is a huge number. If you think of n as 100, this is almost like saying there is a function in 100 bits, which requires 2 to the 100 over 100 gates. And 2 to the 100 is a humongous number. Okay. All right, so let's prove this. And we kind of did almost 75% of the proof last class. We said the idea was to compare the set all n, which is set of all functions versus size of s, which is all functions computable by Okay, we are back online. Okay, so we're just going to count the two and compare the two, right? So all n versus size of s. And in last class, we saw that this number is exactly 2 to the 2 to the n, right? And we also saw that this is at most 2 times 2 to the 12 times n plus s times log 2 n plus s. Okay, so we have these two things. And if we show that 2 to the 2 to the n is strictly bigger than the other number, then we are done, right? That means that there are functions which cannot be computed by circuits of that size. Okay, so now is just some arithmetic to kind of simplify this expression. Yeah.
So I noticed proof is on like our definition for our encoding. Like, did we prove that this is the best encoding?
Not really. I mean, it's not the best encoding. In fact, you can do slightly better, but not too much better.
So if the encoding is better, doesn't that mean that the constant could be larger?
Yeah, so the constant could be larger. I mean, this 12 could be smaller. That's what you mean, right? You know, the constant here could be smaller. The constant C in the lower bound could be bigger.
I guess my question is like, our proof hinges on the fact that our encoding for size S is asymptotically the best we can get.
Yeah,
And is that true?
that's true.
Okay.
Yeah, I mean, okay, so I'll say a few words about it towards the end, okay? So we have this 2 to the 12 times n plus s times log of n plus s. We just had to do some arithmetic to plug what we want. And what is the theorem we're shooting for? We're shooting for something like c times 2 to the n by n, okay? So I won't like, you know, do the grunt work in front of you. I'll just simplify it while hiding the gory details. I don't think that's important. Okay, I just plugged in, you know, substitute S is C times 2 to the n by n. Okay. So I'll hand wave it a little bit in the sense that I'll skip some steps because it's just tedious computation. So if I were to write it properly, I have this guy. And I can say this is at most 12 times n squared plus c to the 2 to the n divided by n times log base 2. I'm going to simplify this n plus c times 2 to the n by n, the whole thing as just 2 to the n. You know, if I set c to be half, let's say, c is less than or equal to half, then this would be true. Okay, again, we're not shooting for optimal constants. We are okay with constant factors that just drops in the ocean. We are mostly interested in the 2 to the n term, which should really dominate. Okay, and you can see that's where kind of this over n comes from because this cancels this guy now. Okay, so you get this is 12 times n squared plus c times 2 to the n. Okay, any questions about this? Yeah. So this is the entire exponent. So I just wrote down the exponent here and I'm writing n plus this as n squared plus c times 2 to the n by n. Okay, so this part, I just, you know, multiplied n squared here and then divided the whole thing by n. Okay, and log of 2 to the n is exactly n.
So the 1 over within the.
This n is not in the log, right? This outside. Oh, you mean here? Yeah, we're just doing an upper bound, right? I'm putting a less than or equal to here. Okay, so 2 to the n by n is at most 2 to the n. Yeah, yes. As I said, you know, we're okay with losing constants. It's an oversimplification, but it doesn't matter for us. It doesn't hurt us. Okay, does make sense? Any other questions? Yeah, I mean, we could be sharper and try and use even this divided by n, but it doesn't matter for us. I'm just going to ignore it to kind of simplify the calculation. Yeah. C is less than or equal to 1/2. So we're going to choose C, right? We're going to choose a specific value for the constant C. Okay, so we can choose it to be anything. And I'm saying as long as we choose it to be anything less than 1/2, this is going to be true. Right? In fact, we're going to set C to be something like 1/48 or something, and then it will be fine. Okay. Any other questions? All right. So if we go back to our comparison, so we need to compare all n is 2 to the 2 to the n. Number of circuits is less than or equal to 2 raised to the power 12 times n squared plus c times 2 to the n. Okay. I have a charger, but it's only one slot. All right, so we have to compare these two things. And, let us set C equals, let's say, maybe 1/24. Again, constants are not important for us, so I'm okay with it. So then I have to compare 2 to the n versus 2 raised to the power . Yeah, maybe let me write this also big so that you can really see. Okay, just plugged in C equals 1/24. This is one value of the constant that works. And the point is that 2 to the n is really going to dominate whatever this additive 12n squared is. Okay, it's going to be insignificant as n keeps on increasing. Okay, and this by 2 doesn't seem like much, but the fact that it's sitting in the exponent makes a huge difference. Okay, you can compare it. I think if I set n equals 11, left hand side is actually n equals maybe 12 is 4096. Give something better. Okay, so it's 3776. Okay, so at n equals 12 itself, the left hand side is bigger than the right hand side. Okay, and once it becomes bigger, it's going to stay bigger, right? Basically the 2 to the n is just going to dominate this whole thing. All right. For instance, n equals 13. The left hand side is well, it's just 2 to the 12. Oh, 2 to the 12 is right. This is 8192. And the right hand side, if you compute it again, it just becomes 6001.
And n represents the number of inputs?
N represents the number of inputs. Okay. So already when you're looking at inputs, functions on 13 inputs or 12 inputs, there are more functions than the number of circuits, with the constant C being 1/24. Okay. Any questions about this calculation? Again, if you're using big O notation, we can just sweep all of this under the rug and just say that the left-hand side is kind of growing faster than the right-hand side. All right. Okay. So therefore, you can check numerically that if n is bigger than or equal to 12, 2 to the 2 to the n is bigger than all right. So it implies that all n is bigger than size n of s, where s is okay, with the constant being 24, we already see a gap. Okay, any questions about this? Okay, so in conclusion, we get our main theorem. So therefore, there exist functions on n bits that require 2 to the n by 24 times n gates. Okay. And this is not a small number. If you look at 2 to the 20 n, let's say you do it for 50, it's going to be a gigantic number. Okay, it's some atrociously large number. Okay, it's almost what? It's almost 1 trillion. Okay, if I said n equals 50, it's saying that there are functions on 50 bits that require 1 trillion gates. Okay. And if you go to 100, it's just, you cannot write it down that well. Any questions about this stuff?
I guess this is a little less theoretical and more logical, but like, we have 64-bit and 128-bit with processors. Like, do they just only implement functions, very basic ones, so that they can operate in many bits?
So they give you some speedups in terms of the constants, but really, maybe instead of saying your limit is 50 bits, it's going to be something slightly higher. Okay. And just hold on to that. We're actually going to talk about this more general question in a little bit. Okay. Any other comments on this lower bound? So we're just saying that circuits, as good as they are, they have limitations in terms of how well they can represent functions. Okay. And going back to your earlier question about, whether or not our size representation was kind of tight, this lower bound suggests that it's tight. Because remember, as a remark, I said we showed that every Boolean function has a circuit of size n times 2 to the n. Okay. But I also said that, in fact, you can improve it to every function has a circuit of size something like constant times 2 to the n. Okay. We proved a slightly worse bound, which was n times 2 to the n, but I said, the textbook does show this refined bound. So we kind of know the exact complexity up to this constant, not per function. When you talk about all possible functions, we are tight up to these constants. So everything can be computed in something like 10 times 2 to the n divided by n, but there are some functions which require almost as many gates. Okay. Any questions about this? All right. If not, let me stop talking about this lower bound and go a step back to what we were discussing last lecture. Right? So we said this idea of code as data has 2 applications for us. One was to count circuits. which in turn led to our lower bound. And the other one, which is what we're going to discuss now, is this notion of universal circuits. Okay. So let me also say a couple of things about this lower bound that we showed. So all the research in computers that there are functions which require exponential number of gates, like 2 to the n by 24 times n. Okay. In fact, most functions, if you do the counting argument right, a random function will satisfy something like this. But we do not know a specific function which requires more than 3 times n gates. Okay. Like, we think multiplication needs at least n log n gates. We do not know how to show it. We think factorization will require some sub-exponential number of gates. We do not know how to show it. Okay. Can take any problem that you might have seen in the last part of CS 180, like, clique, coloring, all of those things. They require, they require a lot of gates. We think they require a lot of gates, but we do not know how to show it. The best lower bound, the best explicit lower bound, explicit meaning for a function that no one can define that requires many gates is something like 3 times n. It's an atrociously small number compared to the 2 to the n that we have. Okay. That's the state of affairs, just because some of proving circuit lower bounds is very non-trivial. Okay. All right. So let's now switch gears a little bit and explore this idea of using code as data. So what did we do so far? We have a circuit. C, and we map it to a Boolean string. Right? You encode it completely as some 0, 1, 0, 1 sequence. Okay. Now, what do you do most often when you actually have a circuit? Right? So what you do with the circuit is you evaluate it on some input. You have a circuit for multiplication. I'm going to feed it some inputs and compute the product of 2 numbers. Okay. I have a circuit for addition. I give it some numbers and compute the addition. Right. That's my, the point of having the circuit is exactly that. So let's write it down. You have some other input. This is the input. Let's call it X, and kind of you feed the input into the circuit, and together you should compute C of X. Okay, so that's our kind of goal. So we want to compute C of X. So you propagate the values through the circuit, and you end up with this guy. Okay. So we have a circuit C of n inputs, and X an input, and we get back C of X. Okay. But on the other hand, if you think of the circuit itself as a Boolean string and S gates, it has a specific encoding, right? Now we can define a function which takes the description of the circuit and the input and gives me the output. Okay. So we are now taking the circuit's description as the input, and I am kind of the compiler, interpreter, or runtime machine, which is going to do the evaluation for you, right? So this is exactly what a C compiler does, right? You take your C program, give it as input to the compiler. along with maybe your arguments, and will tell you the output. Right? So that's the purpose of a compiler. And in the same way, we're going to think of designing a compiler for circuits, right? So let me define this function, which I'll call eval. Okay. So we know the circuit C of n inputs and S gates can be represented as a string, 0, 1 star. Now maybe of some number of bits. Let's just call it S of S. We have a bound depending on our encoding. It's not too important what that is, but we have some bound. Actually, let me say S of n comma S. Okay, I'm now specifying or defining a new function which takes two strings as input, interprets the first string as a description of a circuit, the second string as the input, and evaluates the circuit on the input. Okay. Does this make sense? Okay, this is exactly what a compiler does, right? You know, compiler takes a program and an input and then gives you the output. Right? So I'll just say is, so to specify a function, I have to tell you its value on all possible inputs, right? But maybe some strings do not correspond to circuits, right? Because the way we defined the encoding of circuits was very special. Every circuit corresponded to a string, but not all strings would correspond to valid circuits, right? The same thing happens in any programming language, right? Every program is at the end of the day some text file, but if I just put in some garbage characters in it, that's not going to be a valid program. So what does the compiler do in this case? It just gives you some error, right? Any convention for that, it doesn't, we'll just say, you know, for brevity, I'll just choose some default value. So say question. What if we don't have valid circuit encoding? Okay, ideally, your program should kind of warn you, evaluator should warn you about it. But for us, let's just keep it. If it's a valid circuit, it gives you that. Otherwise, it just gives you 0. Okay. All right. And all of this, you can also extend not just to 1-bit functions, but to multiple bit functions, right? And if I put an M here, nothing really changes. You know, maybe my size itself will depend on this guy. And maybe here, to be consistent, I'll put M bits. Okay. So it doesn't matter what the circuit is outputting. What my compiler or evaluator should do is take the description, the input, and spit out the output. That's all. Okay, you can think of this as some kind of meta circuit, which we can use to evaluate all circuits of certain size. Okay, and now mind bending it, we'll get to that later on, but something still somewhat circular. Do you think we can design a circuit to evaluate the evaluate function? Okay, this is like saying, okay, can I write a compiler for the C language in C? Do you think it can be done? Yes or no? Yeah? Mm-hmm. Right. So the way to sidestep that a little, at least in the context of circuits, is the following. So what I'm going to do is I'm going to give my compiler more resources than the programs that it is trying to compile. Okay, which is not a big cheat, right? And you can imagine, okay, I'm giving you the task of evaluating all possible programs. So I might as well give you a little bit more resources. Okay, so maybe then you can potentially do it, right? So does evaluator function have a Boolean circuit? It is some function on some specified number of inputs. Can it be computed by a Boolean circuit? What do you think? There's one answer that we saw a couple of lectures ago, which is that, well, every function has a circuit. So in particular, even this compiler thing is a function at the end of the day, right? So even that will have a circuit computing it. Okay, so this kind of leads us to something seemingly contradictory, but we will identify why it is not contradictory in a second. There is a Boolean circuit that computes eval. Okay, so the input to eval is kind of longer than the n bits, right? So eval has inputs of length the s function, which kind of is determined by the encoding, right? Plus n corresponding to the new input. Okay. So this is a function which takes these many inputs and gives the output. It's just some function now. And we know that for any function, right? If I take this function is giving some output, I can go back to its own truth table, figure out our construction from a couple of lectures ago, and conclude that there is some circuit for it. Okay. Why is this kind of puzzling, or I think should be somewhat contradictory in its nature, is the following. What is it saying? It's saying, imagine I have the inputs here, inputs to the eval function. Okay, the input is kind of logically broken up into two pieces, one corresponding to the representation of the circuit, right? And then the input that we want the circuit to be evaluated on. Okay, this is kind of the logical split. And we're saying there is some circuit. The circuit is never going to change. Maybe it has something like this. Okay, let's do NAND circuit. Okay, and it has some outputs. And once I kind of print this circuit, I can simulate any other circuit just by changing how to set these values. Okay. Does this make sense? Like, basically, if I give you some resources and I tell you, okay, you have the ability to print down one circuit and one circuit only, which circuit would you print down? You're not going to write down the circuit for, multiplication, because then you won't be able to do anything else. You would spend all your resources or your one shot on printing on laying down the wires for this one circuit, the evaluator circuit. And once you put that down, you don't have to change any of the wires. You only change how these inputs are set to simulate any other circuit. Okay. And this is very important in modern architectures, actually, because you really have some abilities to do universal circuits implicit in all of the programming languages. Okay. Once you have that, you can rewire. You don't have to rewire. You only have to change the inputs that you plug in. Yeah. Okay, we are switching to iPad audio. So bear with us. Okay, so there's a theorem saying that there is a circuit for eval NMS, for evaluating circuits which take n inputs, m outputs, and the number of gates is at most s. And the size is s squared times log s. Okay, there is one circuit of size quadratic in the circuits that you want to simulate, and it can simulate all circuits. Okay, so this cost of going from s to s squared, there's only a single circuit that you need to put down, and everything else up to size s can be simulated efficient on this circuit. Okay, so we are not going to prove this. Okay, any questions about this statement? Yeah. The textbook gives kind of a, I would say, pretty good proof of it. I don't think it goes into as much detail as some of the other proofs in the textbook, but it goes into pretty much most of the main ideas. Okay, yeah.
So it's completely independent of NNM.
There is some dependence. Again, just think that S is at least n comma m. Okay, so there is some again, depends on how you count the number of gates. So let's just assume that it's bigger than n and m. Good question. Okay, but I still find it amazing that it's only a quadratic blow-up, right? You can improve it even further if you want to, but you're simulating all possible circuits with only one circuit, and the cost is only quadratic. Okay, that's a really cool thing about circuits. And as I said, this kind of universal evaluator gets used a lot in various cryptographic protocols as well. Okay, so that's all I wanted to say about circuits. Let me summarize why, let me just say why we started, what we did for circuits and why we started studying them. Okay, summary of circuits. We said they're kind of a very simple natural model, which is physically implementable, right? That was one of the main reasons why we started looking at them. Circuits can be implemented on physical devices. Okay, in fact, most modern silicon architectures really rely on implementing basic operations, maybe not as basic as and ors, but more sophisticated ones like addition, multiplication, some number of bits, and then using that as building blocks to run higher level programs. Okay, and even though it's a very simple model, in terms of its description, right? And all this said was you have a basic set of operations and or not, and then you can put them together using any DAG. And this gave us the power to compute any function. As long as we had enough number of gates, right? And there was a counterpoint, which is that some functions require exponential size circuits. Okay. And finally, it's a nice model which allows us to do universal circuits. Right, so there exists a circuit of size something like s squared log s that can simulate all sizes circuits. Your simulate means without rewiring anything, just change the inputs, just set how the initial state kind of initial set of bits are set, and then you get any other circuit. Okay, so these 4 points kind of are threads that we'll see for various models of computation. We study them for circuits. When we talk about other models, you should think, okay, is this model of computation something that corresponds to what we see in reality? Is this something implementable? Is it, are there limitations in terms of efficiency? And then you should always ask, is there kind of universal circuit? Is there one thing which can simulate everything else? Okay. So various other models that we will look at in the rest of the course will again kind of revisit these sorts of questions. Okay, it's kind of similar questions which will mean different things and will give different answers for different models. All right. But before going on, let me say something about these physical devices. And even though this is not something that we cover in this course, maybe at some point later on, I'll change the course to even include some quantum computing. But among all the models we discuss in this class, circuits are the one which are easiest to generalize to quantum computing. And there, you should really think of what you're doing is changing your basic operations. Okay, instead of choosing AND or, now someone gives you some sort of black box device, which we'll call a quantum AND or some quantum gate. Okay, in fact, the quintessential gate is called the Hadamard gate. And once you have that, everything else is kind of the same. Okay, all the other reasonings stay the same. You just change what are the basic operations. Okay, just for the definition, everything else changes. All the physics and everything changes, but in terms of definitions, the only thing that changes is a set of basic operations. All right. And regarding this physical devices concept, you were asking about what if I have something that, right? There is this belief. It's not a theorem. It's not even close to it. It's just like a hypothesis. It's not even like the same stage as like physicists call laws. It's just like a conjecture which we believe to be true, and that's the following. Just call the physical extended Church-Turing thesis, or PECTT. Okay, so it's going to be a mouthful, but the summary is the following. The belief, by and large, is that circuits, are good for some, describing some kind of task. Maybe they're not so great for describing other kinds of tasks. But by and large, if you think of any model that's physically implementable, circuits are close to as efficient as possible. Okay, it's kind of a very grand, seemingly grand conjecture, but everything that people have thrown at it, it has stood it. Okay, so if a function f on n bits, let's say, again, we're going to only look at 1-bit output functions just for simplicity, can be computed by using S physical resources, then it can be computed by circuits that use roughly S gates. Okay, so I would highlight this two things. So you can imagine crazy models of computation, but as long as you think that model kind of corresponds to the laws of physics as we know it, we believe it can be simulated with roughly the same efficiency by using circuits. The gates need to be slightly extended. You need to allow quantum gates, but if you're sticking to classical physics, and this would be true with what we saw, if you're allowing quantum physics, then you just have to allow quantum gates there. Okay. And people have kind of, tried to propose all kinds of theoretical models which might go around it. So for example, there's this thing called soap bubble computation, where soap bubbles solve some very efficient, very challenging combinatorial optimization problems, because you can imagine putting some pegs on a board, dipping it in soap and getting it out. Then the bubbles, they solve a complex surface tension minimization problem, which can be made to correspond to some nice combinatorial optimization questions. Okay, and they kind of seem to solve it in an instant, whereas a computer might require a lot of time to solve it. If I give this configuration to a computer and ask it to figure out, okay, what position will the soap bubbles end up in, it will take a long time for it to compute. You put it in soap and get it out, you have the result right in front of you, right? So what's the catch? Why is this not violating the PECTT, the physical extended church-Turing thesis? Why do you think this is not violating our hypothesis that circuits are as efficient as it gets? Yeah? Yeah, so kind of like that, but you can also be a bit more precise. So, it's doing some computation. I agree, it's doing some computation very fast, but most of the time it's going to be useless computation, right? In the sense, I have a task that I want to perform, and I want my soap bubbles to do it as well, right? So I need to decide where to put the pegs, right? I need to decide how to kind of set up the board so that the answer will be what I need. But how do you know how to set up those pegs? Okay, if someone told me that, of course it does it instantly, but to decide where to put it, to translate from the input to this encoding takes a lot of time. Okay, so that's kind of the catch when people say, oh, soap bubbles can solve all computation. That's the issue there. All right. So we need to decide, we need to configure it. And that takes resources. And people have proposed something called DNA computing. And again, here the idea is that if you think of bits, the storage that you can do with bits has some limits to the amount of information you can store per unit of measurement. I think it's something like if I use 0, 1 bits on any of our fancy, like, flash drives or whatever, something like 10 to the 10 bits per nanometer, whereas DNA strings can store something like 10 to the 16. Something like 10 to the 16 bits per nanometer. Okay, and people are actually doing it. There are various companies which are trying to implement DNA hard drives and so on, because they give you, significantly denser way to store information. Okay, here we're measuring density in terms of the amount of bits per nanometer. Okay, how much information can you store in as small a space as possible? That's great, but at the end of the day, it's still like, some constant factor, right? When we think of this statement, this conjecture, it's not, I'm not saying, okay, for 100 bits or 1,000 bits, it's like, you have to take for a sufficiently large number of inputs, we think the speed up you'll see won't be that significant. All right. And then the craziest thing that people have proposed is something called time travel computing. Again, this is a real theory. It's not just something out of Doctor Who. It's more reasoned than that. I can, tell you that I'm a fan of Doctor Who. And so what's the idea here? At 1:01 p.m. and trying to solve some computation problem, some input X. Okay, I load this input at this time into a machine which is traveling at close to the speed of light. I do my computation on the machine for 10 years on the machine, but then I spit out the answer at something like 1 or 2 p.m.
This is the same thing that they demonstrated in Planet of the Apes, where they fly and 1,000 years pass or whatever, and it's only a year for them, etc.
And what computational problem were they solving? Of course, we can't accelerate things that fast yet. But does it violate our thesis that within a minute you're kind of simulating 10 years of computation? So what's the catch? Why are we not violating our thesis here? Any guesses?
So we're still fundamentally doing all that calculation. We're just taking advantage of relativity to make it seem shorter for us.
Right, but it is shorter for us.
Sure.
Yeah. Yeah, it's not time travel, but you're exactly right that accelerating requires physical resources. Okay. In fact, people have done this back of the envelope calculations to say, okay, suppose I want to compute on n bits. What's the minimum amount of space I need to store that? And if I want to accelerate it to maybe 0.99 times the speed of light, how much energy do I need? And how much time would I need to accumulate that much energy? You take all of that into account, you end up with the same circuit size. Okay. So you take into account all of those things. At the end, you end up with the same amount of computation time as your circuit is taking. Okay. So you have to, when people say things are happening very fast, you have to dig deeper and see, okay, are they just hiding the real cost somewhere else? Okay. So this kind of grand conjecture seems to stand everything that we at least have for now in the laws of physics. And what we're going to do next is kind of go beyond one limitation, the most important limitation that circuits have. And we'll talk about that and what follows, how to correct it. After the break in 5 minutes.
Professor, there's no audio.